Are you waiting for me?
No.
Okay.
Adrián.
Okay, so welcome to this seminar. Bienvenidos al seminario de estudiantes de posgrado de probabilidad. Estamos muy contentos de tener a Samuel Johnston el día de hoy, a quien Sandra va a presentar, pero les recuerdo de qué se trata la dinámica del seminario. Este es el seminario de estudiantes de posgrado en el que cada estudiante elige un artículo, lo lee, nos lo explica, y la semana siguiente uno de los autores del artículo viene y nos platica sobre él. Adelante, Sandra.
So thank you. It is my pleasure to present Samuel Johnston. He did his PhD at the University of Bath with Matt Roberts and Simon Harvard. After that, he went to Dublin to do a postdoc with Neil O'Connell, and another one at the University of Graz with Joshua Prof. Now he is working again at the University of Bath in fragmentation coalescent processes with Andreas Cipriano and Tim Roberts. So thank you for your presentations.
Thank you very much, Sandra. Adrian, thank you for the opportunity to speak. Thanks, Iram, as well. And thank you all for coming to listen. So I'm going to be talking about multi-type lambda-coalescence. And this is a joint work with my supervisors, Andreas Cipriano and Tim Rogers. So can everyone see my cursor, by the way?
Yes, we can see it.
Great. So before talking about multi-type lambda coalescence, we need to talk about coalescent processes. And before talking about coalescent processes, we need to introduce partitions, just so everyone's on the same page. So a partition of a set A is a way of breaking this set A into lots of pieces, basically. So more specifically, a partition of a set A is a collection of subsets of A that are non-empty, they're disjoint, and their union is all of A. Now, if we have a partition of a set, we can create new partitions of sets by merging the blocks together. So whenever pi and pi dash are partitions of A, we say that pi dash is bigger than pi if every block of pi dash is a union of blocks of pi. So this is best seen with an example. Here we have two different partitions of the numbers 1 up to 6. And these partitions are pi and pi dash. And pi dash can be obtained from pi by merging together the first two blocks. So we have some operations we can do on partitions. So whenever we have a partition of a set A and a bijection, sigma, acting on A, we can create a new partition, sigma pi, by letting sigma act on each of the blocks individually. So more specifically, gamma is a block of the original partition pi, if and only if sigma gamma, where we just let sigma act on each of the elements of gamma, is a block of sigma pi. So that's one way of taking a partition and creating a new partition. Another way is when we have a partition of a set A and a subset B of A, we can project the partition from the bigger set down onto the smaller set by just restricting all of the blocks to their overlap with the smaller set B. So we have permutations and projections of partitions. And here's an example of a projection of a partition. So again, we have our partition pi of the numbers 1 up to 6. And we project the partition down onto the numbers 1, 2, 3, and 4. And we break it up. And that way we can create a partition on the numbers 1, 2, 3, and 4. So that's just some basic definitions about partitions. I haven't actually spoken about any probability yet, and this is a probability seminar after all. So we're now ready to introduce coalescent processes. So a coalescent process is simply a stochastic process taking values in the set of partitions of a set with the property that the blocks merge as time passes. So whenever t dash is a bigger time than t, pi t dash is a bigger partition than pi of t. This just means that it's a partition value stochastic process with the property that the blocks merge together, they clump together as time passes. So here's a picture of a coalescent process taking values in the set of partitions of the numbers 1 up to 6. We start off at time 0 with the singletons. So the process starts with breaking the numbers 1 up to 6 into 6 blocks, just containing 1 integer each. And as time passes, these blocks merge together. So if we look at this snapshot in time along this kind of vertical cross section, we see that there are 2 blocks in the system, this one and this one. This first block here contains the numbers 1, 2, 4, and 6, and the other block contains 3 and 5. So simply put, we can kind of draw these coalescent processes as these sort of continuous time trees, where the branches come together as time passes. Now, the most famous example of a coalescent process is Kingmans coalescent. And I know there's a lot going on this slide, but it's fairly simple. So Kingmans coalescent is a coalescent process taking values in the set of partitions of a set A. It starts off with the singletons, and it's defined by the simple property that every pair of blocks merges at rate 1. And by this, I mean that when we have n blocks in the system, there are n choose 2 possible pairs of blocks. So this is the total rate at which events happen in the system. So here's a picture, again, of Kingmans coalescent on the set of numbers between 1 and 8. It starts off with these 8 singletons, and then we have these pairwise mergers as time passes. So Kingmans coalescent has 2 very nice properties. I'm not sure if that's in the way. So Kingmans coalescent is exchangeable and consistent. And I'll explain what I mean by these words now. So let's start off with an informal definition. So we say a coalescent process is exchangeable, a coalescent process on a set A, if all of the different elements of the set A are treated equivalently. So 3 is kind of the same as 2, 6 is the same as 1, etc. So in Kingmans coalescent, every pair of blocks merges at unit rate. It doesn't matter which elements are contained in which blocks. All of the blocks are treated equally. That's an informal definition of exchangeability. Giving an informal definition of consistency, this definition is a bit harder to understand, but well, I always find it slightly more subtle. But a coalescent process is consistent if we can look at any projection of the process onto a smaller subset, and we know how fast the projection onto the smaller subset, we know how fast the blocks of the projection merge. I'll give some examples of this in a second. So here we have a picture of Kingmans coalescent on the numbers 1 up to 7. And if we project the process onto the numbers 1, 2, 3, and 4, we still have a simple, nice Markov process where we understand how fast the blocks of the projection onto 1, 2, 3, and 4 are merging. Okay, so those are kind of rough definitions. I'll now be a bit more precise before giving some examples. So here we say in Kingmans coalescent, we can restrict our attention to the projection and we still have these simple pairwise mergers. Okay, so let me give the more precise mathematical definition. So more rigorously, Kingmans coalescent is exchangeable and consistent, where we say a coalescent process is exchangeable if it starts off taking values in the singletons of a set, and its distribution is invariant under bijections of the set. So this essentially means that all of the different elements of the set are treated equivalently. Now, a coalescent process is consistent if for every subset B of the set, the projection is a Markov process in its own filtration. Now, this is quite an abstract definition the first time you see it. In order to get a good understanding of these two definitions here, it's useful to look at some examples of some coalescent processes that don't have these nice properties. So obviously, I've just said that Kingmans coalescent is a very nice coalescent process that does have these properties. But now we can look at some examples of processes which don't have these properties. So here's an example of a coalescent process which is exchangeable but isn't consistent. So let's suppose we have a finite set and we have a coalescent process defined on the set of partitions of this finite set. And it's got the property that blocks merge, a pair of blocks gamma and gamma prime merge at a rate proportional to the sum of their elements. So this means that bigger blocks merge more quickly than smaller blocks. Now, this process here is exchangeable because all of the elements of the set A are treated equally or equivalently. However, this process is not consistent because whenever we take a subset B of A, we're not sure how fast the blocks of the projection onto B merge without knowing what blocks they correspond to the larger partition of the larger set A. So it's not consistent. So there's an example of a process that is exchangeable but not consistent. Here's another example of an exchangeable but not consistent process. Let's take a coalescent process on the numbers 1 up to n. It starts from the singletons, and it has the property that every triplet of blocks are merging at unit rate. So in this process here, when there are n blocks, the total merge rate is n choose 3. So you'll see here that we start off with 11 blocks, 3 merge over here, and 3 over here, etc., until we have 1 block left. Now, again, this process is exchangeable because all of the different elements, all the different numbers 1 up to 11 are treated equally. They're equivalent to one another. However, this process is not consistent. And to see this, you'll note that if you look at, say, the numbers 4 and 6, if we look at the projection of this process onto the pair of numbers 4 and 6, and we're interested in how fast or how soon 4 and 6 are contained in the same block, then the speed at which 4 and 6 join the same block is equal to the number of other blocks in the system. So we need to kind of know about the rest of the system to know how quickly any 2 pair of blocks are merging. So it's not true that when we look at a projection of this process onto a smaller set, that it's a Markov process in its own filtration. It's not true that we know the rates of the projections of the process. So here's conversely an example of a process that's consistent but not exchangeable. So let's fix any element of the set A, and we define a coalescent process by similar rules to Kingmans coalescent. Every pair of blocks merges at rate 1, apart from if one of these blocks is equal to the singleton A0. The singleton A0 is not allowed to merge with any of the other blocks. Okay, this is a coalescent process. The blocks merge as time passes. However, it's clearly not exchangeable because the elements of A aren't being treated in the same way. The element A0 isn't allowed to merge with the other blocks, but the other elements are. However, this process is consistent. So we know that for every subset B of A, we know exactly how fast the blocks of the projection onto B merge. And we don't need to know how, we know exactly how fast the blocks of the projection merge without having to know about the full partition on the set A. So it's consistent. Here's a final example of a really bad process which doesn't have either of these nice properties. So let A be a finite set, and let lambda A be a collection of non-negative real numbers. We can define a coalescent process on the set A by letting it start off from the singletons, and then we let each pair of blocks, gamma and gamma prime, merge at this rate. So it's a sum over these rates, and it's a sum over the elements in both blocks. It's clearly not true, unless all of the lambda A's are the same. If we assume that those lambda A's aren't the same, then it's clearly not true that the elements of A are being treated in the same way. So this process isn't exchangeable. It's also not true that we know how fast the blocks of a projection merge without knowing the partition structure on the full set A, because the speed at which the mergers happen depend on the other elements in the set. So there we've seen 4 examples of some coalescent processes that fail to have these nice properties. But in summary, a coalescent process is exchangeable and consistent if the blocks merge at a rate that doesn't depend on what's contained in the blocks, all of the blocks are treated equally, and we can look at any subset of the blocks and we know how fast they merge without having to know about all of the other blocks in the system. So can we find examples of other exchangeable and consistent coalescent processes? We've seen that Kingman has these nice properties, but can we find some other examples? And in fact, can we do even better? Can we classify the entire possibilities for these exchangeable and consistent coalescent processes? So with a view to answering these questions, let's look at another example. So I'll call this the delta P coalescent. So this is a coalescent process on a set A with the property according to a Poisson process of rate 1, we have these large merger events happening. So we have a Poisson process on the time axis here, and at each of these events, some of the blocks are involved in the merger and other blocks aren't. More specifically, at each one of these events, every block in the system flips a coin with a probability P of being heads. If it's heads, they join in on the merger, and if it's tails, they ignore the merger and they stay on their own. So here in this first merger, 4 out of the 10 blocks were involved. Then at the second merger, 3 out of 7 blocks were involved, etc. So this process here, it is exchangeable and consistent. It's exchangeable because all of the different elements of the set A are treated equivalently. And it's consistent because we can look at any subset of the blocks and we know how fast they come together without having to know about the other blocks in the system. Here's a more complicated example that's a generalization of the previous example. Let's let Q be a measure on 0, 1. Then I've written this I haven't explained this in a huge amount of detail, but here's a brief sentence. At rate Q ds, an S merger event occurs. So the kind of short story here is that according to a Poisson process on the time axis, these merger events happen, but these merger events can have different probabilities. So here we have, they can have a random probability of being involved. So here we have our first point occurring, and the probability of being involved in this merger is 0.4. So 3 out of the 10 blocks are involved. Then the probability of being in this next merger is 0.6, and more of the blocks are involved, etc. So we have these Q coalescents where large merger events happen according to a Poisson process, and the probability of each block being involved in the process can be random. And in fact, we can let this measure Q be infinite, as long as lots of the mergers are really small. So we've seen two main examples of exchangeable and consistent coalescent processes so far. We've seen the Kingman coalescent, and we've seen this Q coalescent here. And we're now ready to state the famous result of Pitman classifying all of the exchangeable and consistent coalescent processes. So Pitmans' result says that if we have an exchangeable and consistent coalescent process with no simultaneous mergers, and I won't go into too much detail about no simultaneous mergers, but it just means that you never have two separate groups of blocks merging to form two different blocks at exactly the same time. But whenever we have an exchangeable and consistent coalescent process with no simultaneous mergers, then roughly speaking, this process has to be a mixture of a Kingman coalescent with some rate ρ and a Q coalescent with some measure Q. So let's suppose that there are B blocks in the system at some moment, and we're interested in the rate at which any subset of the K blocks merge to form a single block. Then this rate is given by this thing, lambda bk, where this term here comes from the Kingman component, and this term here comes from these large Q measures, these large Q events. And just explaining this integral here, whenever we have one of these S merger events, the probability that the K blocks, our K favorite blocks, are involved is S to the K, and the probability that the B minus K other blocks are not involved is 1 minus S to the B minus K. So this integral here captures the overall rate at which K blocks merge due to these Q events. Now, I've written this theorem here in a kind of slightly unusual way. So let me just explain how it's usually written. So we recall from the previous slide that we have this ρ Q coalescent, and the rate at which K out of the B blocks is given by this formula here. We can define a measure on 0, 1 by this thing here, where that's the Dirac mass, and we take S squared times Q ds. Then the ρ Q coalescent is usually called the lambda coalescent, and the merger rates can be written in this simple form as one integral. So that kind of completes the single type part of our story. Does anyone have any questions in the chat? Please just interrupt me. Okay.
No.
Okay. So we're now ready to talk about multi-type coalescent processes and multi-type partitions. So before jumping into a definition of a multi-type partition, it's useful to kind of look at the type of processes we want to understand. So we want to understand these sort of multi-type coalescent processes. They're processes that have these blocks, and the blocks merge together as time passes. But the blocks also have colors or types. So here you'll see we have this one green block, and at this moment it decides to change color and become yellow. Here we have a yellow block that turns green and another green block. They merge together to form a new green block, and etc. We have blocks of various colors or types, and they can merge and change color and change type, etc. I'm using the words color and type to mean the same thing. Now, if we look at a snapshot of this process at time t, we have what's called a multi-type partition. So here we have a partition of the numbers 1 up to 7, but each block in the partition has a color. So we have some yellow blocks and some green blocks. So here we have a yellow block containing the numbers 1, 3, 5, and 7. Okay, so let's be more specific about what we mean by a multi-type partition. So simply put, a d-type partition of a set is a d-tuple of disjoint collections of subsets of A such that pi hat is a partition of A. That was a really long sentence, but in essence, a d-type partition is simply a partition where every block has a color, and the color is a label ranging from 1 to D. And here's an example of a d-type partition or a 2-type partition. So here we have the numbers 1 up to 7. And we have a partition on the numbers 1 up to 7. We have a block 137 of type 1 and a block 2 of type 1. And we have another block 456 that has type 2. So the pair pi1, pi2 is a 2-type partition of 1 up to 7. So a d-type coalescent process is simply a stochastic process taking values in the set of d-type partitions with the property that the blocks merge as time passes. Now, we're going to talk about exchangeability of d-type coalescent processes and consistency of d-type coalescent processes in a moment. In order to do this, we need to, again, define how permutations and projections act on these d-type partitions. So when we have a d-type partition of a set A and a bijection acting on A, again, we can let the bijection act on each of the blocks individually. And this creates a new d-type partition. Again, if we have a d-type partition of a set A and a subset B of A, we can define a new d-type partition of the smaller subset B by just restricting all of the blocks to their overlap with B. So now that we have an idea of these d-type partitions in mind, let's look at a d-type version of Kingmans coalescent. So this was introduced by Notohara around 30 years ago, I think. So in the d-type Kingmans coalescent, every pair of blocks that have the same type can merge to form a new block of that type at a certain rate. And I write this rate rho I to I. So that's the rate at which 2 i's become 1 I. We also have single blocks changing color. So each block of type I can change to type J at rate rho I to J. Now, just informally speaking, this process is exchangeable and consistent. It's exchangeable because blocks of the same type act equivalently. So not all of the blocks are the same, but blocks that have the same color are equivalent. And also the projections of the process are Markovian. So being more specific here, and this first bullet point is, I know it's quite a lot to read, but the rigorous definition for d-type exchangeability is that the process is invariant under bijections that map the same blocks, bijections among blocks of the same type. So it's a bit of a mouthful, but whenever we have a coalescent process that starts from the singletons, then the distribution of this coalescent process is invariant under the action of any bijection that changes the singletons of the same type. All this essentially means, big picture, is that blocks of the same type are equivalent to one another. And then consistency is similar to how it was before. A d-type coalescent process is consistent if all of its projections are Markov processes in their own filtration.
One question, Sam.
Yeah, sure.
So the seed bank coalescent is an example of a d-type exchangeable coalescent, which you...
Yes, exactly, yep.
This work, okay.
Because so Adrian's referring to an example of a coalescent process with 2 different types. Is that right? And there are active types and dormant types. And if I remember correctly, in this coalescent that Adrian and his co-authors study, there are 2 types where we have these dormant blocks that stay sleeping, and after a certain amount of time, they wake up. Is that right? And then the blocks that are awake can interact with one another. And this is an example of a 2-type coalescent process. Did I give a correct description of it briefly there? Yeah. Yeah. So yeah, the seed bank is an example of a d-type exchangeable and consistent process. So in essence, a d-type coalescent process, taking values in the set of d-type partitions of the set A, is exchangeable and consistent if it doesn't matter what's contained in the blocks and all of the blocks of the same type are treated equivalently. So again, we can ask an analogous question to the one that we asked in the single type case. What are the exchangeable and consistent d-type coalescent processes? So we have our main result here, that if we have a d-type exchangeable consistent coalescent process without simultaneous mergers, then it is a d-type lambda coalescent. However, I haven't given an example, I haven't given a definition of what a d-type lambda coalescent is. So here's the definition, and there's lots of notation here, apologies. And so let lambda be given by this collection of objects, where these row I to j and row ii to I, these are all rates. And then we also have measures qi, and each measure qi is a measure on the unit cube in d dimensions. So a d-type lambda coalescent is a coalescent process where we have blocks of different colors and they merge together and they change color according to the following dynamics. So our first dynamic is that a single block of type I can change type to type j at this rate, row I to j. Now, our next dynamic is that two blocks of the same type are allowed to merge to form a single block of that same type at this rate. And finally, and this is the most complicated part, these measures qi, they're all measures on the unit cube in d dimensions. And according to a certain Poisson process, we have these S merger events of type I occurring. And at this event, so S here is a vector, S1 up to SD. And at one of these S merger events of type I, every single block in the system that has type J independently chooses to be involved in this merger with probability Sj, or not involved with probability 1 minus Sj. And the new block that's created at this merger has type I. Let's see a picture of one of these d-type lambda coalescents. So here I've drawn a d-type lambda coalescent with 3 different types. And we can see the different dynamics that affect how the blocks interact with one another. So here we have 2 black blocks. They merge to form a single black block. And that's according to this rate rho 1, 1 to 1. We can also have a single block changing color. And finally, the most complicated part are these qi events. And so we have a Poisson process, sort of complicated Poisson process on the real line. And at each point of this Poisson process has a color, I, in taking values between 1 and d, and an element S of the unit cube that describe the involvement probabilities in the merger. So here you'll see there was one of these events, and these 2 yellow blocks chose to become involved in a merger to create a new blue block. But all of these other black blocks and this blue block here ignored this merger. A bit later, we had one of these, another merger to create a new black block, and some black blocks were involved in this merger. A blue block was involved in this merger, but these 2 blocks that are blue and black weren't involved. So in essence, there's a lot of notation flying around, but in essence, a d-type lambda coalescent is a process with single blocks changing type, pairwise mergers within the same type. So you can only have 2 blocks of the same type merging to form a new block of that type. And then we also have these larger mergers, and the larger mergers create a new block of a certain color, and they have certain probabilities for whether different blocks of different colors are going to be involved. So our main result on the a couple of slides ago was that if a d-type coalescent process is consistent and exchangeable, then it has to be one of these lambda coalescents, one of these d-type lambda coalescents. So there has to be these rates rho I to I, rho I to j, and measures q to I that classify this behavior. And as Adrian mentioned before, the seed bank coalescent is an example of a two-type lambda coalescent, as is the multi-type Kingman coalescent that I mentioned a few slides ago that was studied by Notohara. And there have been other examples of sort of multi-type lambda coalescents that fit into this framework. So the last chapter of this talk is on something that's slightly different in flavor to what I've been discussing so far. So far I've been mainly discussing these properties of exchangeability and consistency. But now I want to talk about something slightly different, and that's the property of coming down from infinity. And I won't go into a huge amount of detail here, but just I'll give a brief review. So a single type coalescent process comes down from infinity if, even when it starts with infinitely many blocks, after a finite amount of time, there are finitely many blocks. So this picture here is courtesy of Wikipedia or Wikimedia. Here we have a Kingman coalescent starting with 50 blocks. And you can see that quite quickly, all of these blocks come together. And so that after some time, there are only 3 blocks. It turns out that even if we started this simulation of Kingman's coalescent, instead of 50 blocks, we chose 50,000 blocks, the picture would still look quite similar. That actually all of these mergers would happen really fast near the beginning. And that's because when you have n blocks, the rate of mergers is n choose 2. And that n choose 2 is so big that when n is big, that it all comes together very quickly. So let me actually I'll be a bit more specific here. Let me give a sketch proof of this fact. So when Kingman's coalescent has n blocks, the average rate of decrease in the number of blocks is n choose 2. And n choose 2 is approximately n squared divided by 2. So if we let Vt be the number of blocks, then being very informal and hand-wavy, Vt satisfies this differential equation. The number of blocks decreases at a rate proportion that's roughly minus Vt squared over 2. Now, we can just pretend that Vt solves an ordinary differential equation, an ODE, and start it with the initial condition plus infinity. And it turns out when you solve this ODE with initial condition plus infinity, you find out that Vt is approximately equal to 2 on t. Now, this argument here is clearly not very rigorous, but it actually turns out to be correct. So it is true that asymptotically, the number of blocks in a Kingman coalescent, starting with infinitely many blocks, is roughly 2 over t for small times t. And that's because the speed at which the blocks are processed, the speed at which the blocks come together, is equal to n squared over 2, roughly. So the story of lambda coalescents, more general single type lambda coalescents coming down from infinity, is more delicate. So recall that in our single type lambda coalescent, we have these 2 ways of blocks coming together. We have these Kingman style mergers that happen at rate rho, and at rate qds, we have these larger mergers happening, where every block in the system has a probability or a possibility of being involved in a large merger. Now, if rho is bigger than 0, then since Kingman's coalescent comes down from infinity, so does the lambda equals rho q coalescent, because this Kingman coalescent is sort of an engine that's forcing the number of blocks to decrease. However, if rho is equal to 0, the story is a lot more complicated. So let's recall our old friend, the delta P coalescent. So in the delta P coalescent, at rate 1, we have a large merger event with probability P. Now, if M merger events have occurred by time t, and we start with a large number n of blocks, then there are roughly the probability that a single block managed to avoid all of the mergers and not be involved in any of them is 1 minus p to the power m, because it has a probability p of being involved and a probability of 1 minus p of not being involved. This means that, roughly speaking, if we start with a large number n of blocks, then roughly this many blocks have never been involved in a merger, n times 1 minus p to the n. So if we send n to infinity, there are going to be infinitely many blocks in the system. So it's not true that if you start a delta P coalescent with infinitely many blocks, and you look a moment in time later, or you look at a positive time, it's not true that there are going to be finitely many blocks. There will still be infinitely many blocks. So it turns out that this measure Q, if rho is non-zero, this measure Q actually needs to be infinite. And it's a bit complicated. I won't have time to go into the full story here. But just to give an outline of how it works, the expected rate of decrease in the number of blocks in a rho Q coalescent is equal to this entire function here. I'll explain where all of these terms come from. So this first term is the expected decrease in the number of blocks due to the pairwise mergers. This next term, ns, is the expected number of blocks involved in a large S merger. So if we have n blocks and the probability of being involved in a S merger is S, then ns is the expectation of a binomial random variable with parameters n and s. But this last term here is a bit more complicated. This is a subtle effect, but this is the probability that an S merger is non-empty. This is the probability that at least one block is involved in the merger. So this function here characterizes the overall speed at which the blocks decrease. The number of blocks in the system decreases when there are n blocks. And we have this result by Bertone and Legal from 2006, that the rho Q coalescent comes down from infinity only if psi of x is big enough for small x that this integral is finite. So bigger psi means smaller integral, sort of thing. And this integral here between s to infinity of dx over psi x, this can be thought of as, roughly speaking, the amount of time it takes to reduce from infinitely many blocks to S blocks. So again, I don't have too much time to go into detail, but this should give a broad idea that there is some function measuring how fast the number of blocks in the system decreases. And we can use this function to characterize whether the coalescent comes down from infinity. So I'll close my talk by stating an analogous result in the case of the d-type coalescent. So again, we have our d-type coalescent with these three different dynamics: blocks changing color, pairs of blocks merging, and these large mergers of blocks of different colors to form a sumblock of some color. So we say a d-type coalescent comes down from infinity if, starting with infinitely many blocks of each type, so we have infinitely many blue blocks, infinitely many black blocks, infinitely many yellow blocks. We say it comes down from infinity if, starting with infinitely many blocks of each type, when we look at a positive time, the total number of blocks across all types is finite. So we would like to know when these d-type coalescent processes come down from infinity. And to do this, we define this complicated function, which somehow captures how fast the number of type I blocks in the system decreases. We can think of the measure Qi as an engine describing how quickly we process type I blocks in the system. So again, we have this result, which is analogous to Berthelon and Legal's result. So it turns out that the d-type lambda-coalescent comes down from infinity if and only if all of these functions psi ix are big enough that this integral is finite for each I in 1 to d. So roughly speaking, this means every single type of blocks needs a way of getting rid of blocks that's fast enough for the total number of blocks to come down from infinity. And I think I will wrap up there. Thank you very much for listening.
Thank you, Sam. It was very clear. Are there any questions or comments?
Yes, I do. So, Sam, do you have any particular, I mean, what happened when you have multiple merges? Do you need, can you have like an example where you don't have this coming down from infinity? I mean, or is that very difficult to build?
Yeah, if you choose, actually, there are lots of examples of d-type coalescence not coming down from infinity. If you choose any Dirac mass, if you let each of the measures qi be a Dirac mass, then it doesn't come down from infinity. That's the kind of multi-type analog of the delta p coalescent. Yes. Or even if you choose the uniform measure on the unit cube, it doesn't come down from infinity. So each one of the measures qi is a uniform measure. Okay. It turns out that they need to be infinite. The qi measure needs to be, but roughly speaking, for each I, we either need rho ii to I, so that's the rate of two i's merging to form an I. We need that to be positive, or we need the measure qi to be very big in the SI near 0 part of the cube. I know that was a bit of a mouthful, but
okay. Thanks.
Arno?
Thanks, Tracy.
Yes. Thank you very much, Sam, for your talk. I think it's more or less the same question, but about coming down from infinity. So you have examples, I imagine, where all your i's come down from infinity, the measures associated to all the i's makes that the restricted coalescent goes to infinity, and somehow it does not come down from infinity because of this change of the change of type that makes a mess or a mixing phase and makes that the coalescent cannot come down from infinity. Is it a good picture that I have, or?
So if I've understood correctly, are you asking whether it's possible that some types come down from infinity, but other types don't? Yes. Yeah. It seems like there is, this is an interesting question to ask. I don't fully understand what happens, but it seems like you can have quite complicated behavior with some types coming down from infinity and other types not coming down from infinity.
So in the seed part coalescent, for example, it's like this, like you have a Kingman part.
Yep.
And another one which is frozen, but this source of frozen part, like when they start to mix together, it makes that it does not come down from infinity.
Yeah. This is quite interesting, and I think there are very interesting examples where you start with infinitely many of one type of block, and maybe these blocks migrate to form other types, and do those other types come down from infinity? So yeah, I think there is a circle of interesting questions to ask around different types coming down, and I don't have a solid picture in my head of exactly what happens in general. But yeah, thanks for the question.
Thank you.
Thank you, Arno. Are there more questions? Rodrigo?
Yes. So if one wants to simulate this process using a programming language,
yep.
How can you do it? Like, what are the steps? So, like, if I have like row I to I and row j to I and the queues, how can I, simulate that? Like a process, like, an instance. I don't know how.
No, it's an interesting question. I'm not the best person to ask. I'm not very good with computers and programming languages and the like. But are you asking the question in comparison to simulating just a single type Kingman coalescent? Is that right?
Yes. Like I want to understand like the concrete role that those rates play, like from a practical point of view, because it is kind of abstract to me. So maybe like if you have like if you simulate a Poisson process with like rate row, and then like how can
yeah. I think the story is simpler if just simulating it, and maybe this isn't a very good answer, but I think it would be fairly simple to simulate the coalescent with all of the rows equal to 0, but the queues non-zero, because then you can draw a kind of multi-type Poisson process on the real line and then choose which blocks are involved. But yeah, I think it would be quite complicated to simulate it with the rows non-zero, because there are lots of different colors to keep track of. Yeah, I'm not sure. Sorry, it's not a very good answer.
It's fine. Thanks.
No, thank you, Rodrigo.
Adrian?
Yes, so I have a question. So when Pitman does this characterization of the lambda coalescent, there is the extra condition that you can have simultaneous multiple merges, right? So
yeah,
otherwise you get the he, and I guess that this is also hidden somewhere in your work, because this doesn't seem to occur that you have he coalescence.
Yeah, but I guess maybe answering is basically what you're wondering. If you do permit simultaneous mergers, do you have a d-type analog of a C coalescent?
Yeah. So,
yeah, because I've wondered the same thing, but I think we were scared to have a go at proving it because there's already lots of notation. But yeah, it's yeah.
But maybe
sorry,
some other thing that maybe one assumption erased at some point is coordinated changes of type. So in the seed bank story, we have this model where people go to the seed bank and out due to some Poisson event. So maybe at some time, 15% of the population become active, or and kind of things clearly do not destroy exchangeability. They do not destroy consistency either. So,
so actually, yeah, what you've just pointed out is it's even more complicated than the psi-coalescent, isn't it? Because as you say, that
it depends who you ask to. So I think it's way nicer, but maybe somebody that likes coalescent would think otherwise. But
I guess what you've just described, it does technically fit into the framework of being d-type, exchangeable, and consistent. So that's certainly something interesting to think about. So I guess the broader framework would involve some kind of complicated. It's even more complicated than a multi-type psi-coalescent. You can have coordinate.
I was wondering, I mean, we can talk about this later, but I was wondering which assumption removes the possibility of people changing type at the same time. Because you have this characterization theorem that does not include measures to jump from one island to the other. Right? So there should be one point in which you don't allow this to happen.
I think it could be the case that actually that's a technicality that's a mistake in the paper, and you've just raised a good point, because I see what you mean. I'm not sure there is an assumption that rules out what you've just described.
Okay.
So maybe we need to update the paper. Yeah.
I will send you a couple of references regarding coordination, but I think
Great. Yeah. That's an interesting point. Thank you.
Julio?
Hello. I see that you use system, well, an ordinary differential equation to study the number of logs that you have for the Kingman coalescent. My question is if you use a similar approach to multiple when you are taking multiple types, like use a system of differential equations, and if
actually that's a really good question. We don't actually use ordinary differential equations too much in our in the proof of our result on multitype coming down from infinity. However, we make a conjecture in the paper that the speed at which a d-type coalescent comes down from infinity is actually governed by a d-dimensional ordinary differential equation. So I think that'd be something really interesting to look at. Does that kind of answer your question, Julio?
Yes. I was wondering if you can use a system to calculate something in the multiple type.
Yeah. I think so, but technically it seems like a big task. Yeah.
Thank you.
Thank you.
Arno?
Yes, another question. To make the picture more complex even, so I don't know, maybe you chat with Tim about this, but with Tim we did a work with IRAM too on nested coalescence.
Yep.
And in this case, so you lose exchangeability, but you don't lose like totally exchangeability. So it's you have ways to lose a bit of exchangeability, but not everything. And I don't know if you manage to quantify this kind of partially exchangeable things that can happen to, or I don't know if you thought of including the nested coalescence in your pictures. Or...
I'm not actually familiar with the nested coalescent. I probably should be, but I can look into a bit.
Okay. So yeah, these are like imagine like Kingman coalescent, like d-type or many types Kingman coalescent, but also like species, like the you can like merge species so that you don't change your type lineage wise, but you can like decide that everybody like two different types they merge together to be the same type, and then like merging of types, let's say.
Right. Okay. Yeah, I'll have a think about that. Yeah.
Okay.
Sorry, I'm not familiar enough with the literature to give you a good answer.
Yes, I also think that it was included the nested, but you have to condition to be to the same type in your construction. And yes, my question is just to clarify the difficulty to extend your work to have simultaneous coalescence is just not the notation. You are thinking to go to this direction to have simultaneous multiple coalescence?
Yeah,
I think you aim to at some point.
I think we wanted to keep the paper fairly simple, or maybe we were just scared. I'm not sure, but I think I think it should be doable. I'm not actually familiar with the techniques in proving the classification of the Xi coalescence.
Yeah,
and
and another question is in the direction of Julio. It's about the speed of coming down from infinity, because I didn't understand, it was not clear to me if you found it or you didn't.
Oh, we have the formula is a bit complicated to write in the slides. But in the preprint, yeah, we have an explicit guess for the speed at which it comes down from infinity. Yeah.
And just what are the further directions of your work?
I'm not sure yet, but yeah, I guess the simultaneous mergers is something to think about, certainly. Yeah.
Okay. Thank you so much. It was very nice, your talk.
Thank you, Ira.
Are there more questions? Emmanuel?
Oh, yeah. Hi. Is there a relationship between these lambda coalescent multitype with multitype branching processes or frequency processes? Do you know?
Yeah, so there's been some work on the coalescent structure of continuous state branching processes, or actually more simple is, but yeah, so if you take a continuous state branching process, its coalescent structure can be described in terms of lambda coalescent and a single type lambda coalescent. Now, if you take a multi-type continuous state branching process, it turns out that its coalescent structure can be described in terms of a d-type lambda coalescent. So I studied these in a paper with Amaury Lambert, and then I realized that you had these certain d-type coalescent processes emerging. So that's when we with Andreas and Tim, that's when we started to look on actually rigorously classifying these coalescent processes. So yeah, in short, they appear naturally in the coalescent structure of multi-type branching processes.
Okay, thanks. And I know Adrian wants to ask this. Is there a notion of duality here with some process?
God, I don't know. For me personally, I've found duality extremely confusing. I've read the definition like 10 times and I never understand it. But yeah, I'd love to know if there is, yeah, if anyone can spot it.
Okay.
Emmanuel should spot it. Now it's your task.
Oh no.
Okay. Are there more questions? So I have one about your fees and what Emmanuel asked you. So you have a relationship between your coming down from infinity and these CIs.
Yep.
But the CIs are also branching mechanisms, right, or not?
Yeah. So this is also something I understand in the result in this paper by Bertoine and Legal, or maybe it's a collection of 3 papers. They write this thing slightly differently. So they write 1 minus s to the n. Instead, they write it as e to the minus s to the n. Yes. And that means this thing here is exactly a branching process. So they use this to find a connection between continuous state branching processes and lambda coalescence. So in principle, there should be a connection between multi-type continuous state branching processes and multi-type lambda coalescence. But yeah, I'm not sure exactly how it works. But yeah, there should be.
Yeah, so I'm thinking that, sorry, yes.
No, go on, please. I was finished.
So if it is the branching mechanism of a multi-type branching process, then there is a recent paper of, well, maybe it's only on arXiv, of Loïc Chamon and his student. And they say that the process has extinction, like infinite time, if and only if your condition is satisfied.
Oh, right, okay. In the multi-type
maybe
case.
That will relate to what you are doing.
Right, and is that in the multi-type case?
Yes.
Oh, cool. Okay, I'll look into that. Thank you.
So are there more questions or comments?
It was a very nice talk. So thank you very much.
Yes.
Thanks, Adrian.
Thank you very much. So if not, we can thank you. Maybe we can stop the transmission.
I think I did a click